Okay, so we're going to start with module 1, which is then the introduction, orientation, and overview, as I call it. Essentially, we're going to do a fast walkthrough of a lot of the important concepts that we're going to cover in more detail then in the later modules during the course. We're going to start now with a world full of galaxies, as I call it. Discussing various properties of galaxies, and then also scale them up to clusters of galaxy, large-scale structure, and even the universe itself, so to speak. We're going to go to then, in the next block, organizing our own location in the Hubble flow. Where do we sit? And at the end, we're going to just go into some important concepts and numbers that are typically going to be with us for the rest of the course: surface brightness, luminosity function, mass to light ratio specifically. So, a world of galaxies. Now, the first thing then to ask, of course, what is a galaxy? Well, in a sense, that's very easy. We know a galaxy when we see it, so to speak. Most of us have probably seen beautiful pictures of galaxies, and we can identify this is a galaxy, this is a not. Now, a precise definition, though, turns out to be non-trivial. Typically, we say that it's a bound system that contains many stars. So bound here means gravitationally bound. And by that, we can loosely say that I mean something like, okay, we have the sun in our Milky Way galaxy, right? And the sun is not suddenly going to just be shot up and then vanish out into the vast void outside of our Milky Way galaxy. That's not going to happen on reasonably long timescales, because we're gravitationally bound to this system that we call the Milky Way. And that's sort of one thing to think about when we define a galaxy. Now, another thing is that I say that it contains many stars. And this is sort of important in the sense that typically when we think about galaxies, stars provide the main source of luminosity, of radiation that we see. Now, that's true for normal galaxies. As we will see, this is a little bit different when we go to the class of active galaxies. So perhaps we should say, instead of containing many stars, active galaxies also contain many stars, but perhaps the luminosity is also has a very significant component of something else, which we will come to. So perhaps we should see that a galaxy is then something we can see in its radiation, yeah? And that we can see it in radiation is also important, as we will discuss many times during the course, because what we believe is that essentially all galaxies that we know of are embedded into bigger halos, as we call it, of non-luminous matter. And that we know only from its gravitational influence, not from radiation, because, well, then it would be luminous matter. Again, something we will come back to many times during the course. Now, the numbers here in terms of stars is that, say, 10 to the 10. It's a typical number. It can be 10 to the 9, it can be 10 to the 11, but many stars. A typical scales we're talking about for the galaxy here is on the order of for the luminous disk in a system like our own Milky Way. It's about 20 kiloparsecs. That's a rough number, of course. And if you compare this then to the mean distance between galaxies, that's much, much smaller than unity. That's the same sort of effect phenomena that we say that, okay, if we consider the number density of stars in a galaxy in itself, then the extent of a star, our own sun, we can think about the extent, the stellar radius, is much, much smaller than the distance to the next star, Proxima Alpha Centauri in this case, which is like 4 light years, right? That's also true for galaxies. And then most stars in the universe seem to belong to galaxies. The stellar number density in galaxies is much higher than the mean number of stars in the universe. Again, they are, in that sense, an overdensity of stars, galaxies here, right? So in this sense, galaxies are well-defined astronomical objects. But like I said, it's not trivial to make a precise definition, and this is good to keep in your heads throughout the course. On the other hand, like I said, we also know a galaxy when we see it. They're visually clear, they're very beautiful. They're sort of diverse, but they come in distinct sorts as well. Starting with our own, the Milky Way galaxy, if it weren't so darn cloudy here in the night, we might be able to see it, perhaps. But if you are on a good position with a very dark sky, you can see it as this beautiful white stripe in the night sky, as, for example, depicted here. Now, of course, one unique thing with the Milky Way is that we're sitting in it. Typically, we sit at a distance of, say, 8 kiloparsecs or so from its center, from the center of the Milky Way. We sit in one of the spiral arms of the Milky Way as a spiral galaxy, as a disk galaxy. And this makes it very unique in the sense that we can study some parts of it in much greater details than for other galaxies, since we're in it, you know. If we want to study the interstellar medium, the movements of the stars in our neighborhood, etc., we can do that to great detail. Other things, though, are more difficult for us because we sit inside. The analogy I like to use is that, okay, imagine we're sitting here inside this room, right? So I can study some details, some details of this room or this building in quite some details. For example, I know roughly how many we are here in the classroom, you know, what we wear, etc. A lot of these details are very clear for me because I'm standing inside the classroom. But if you ask me, what's the color of the roof of this building? That's not a trivial question. Just because I stand inside, you know, and can look outside there, try to reflect and see that, but it's not trivial. It would be much easier if I just walked outside, looked at the building from outside, and then, yeah, that's the roof. It's easy for me to see. And we can think about this in terms of that some aspects, much easier for us to study in our own Milky Way. Other aspects, actually a little bit more difficult. So, main components here in our Milky Way is indeed the disk, the spiral arms. We have also then a bulge that sits in the center, within it a supermassive black hole, which in the Milky Way specifically, we'll come back to that again, is non-active. And we will see what I mean by that. But also around then the disk of Milky Way, we have a halo, and that is a stellar halo, which has much less stars. They're typically older, and they're centered over in these clouds there that we often call globular clusters of stars in our own galaxy. Now, in turn, these are then situated in a much larger halo that we only can infer indirectly through its gravitational influence on the movements, as we will see, and that we typically then call a dark halo. Yeah. So if we look at the mass inferred, then the mass inferred inside our own sun's orbit here, which is at 8 kiloparsecs or something like that, is something like 10 to the 11 solar masses, which is significant. However, if we go out to, say, 100 parsec, this mass actually increases by an order of magnitude. So the majority of the mass actually sits then outside of this in the Milky Way. That's our current understanding of things. Now, here is now one of the deepest images. This is from the Hubble Extreme Deep Field of the universe, and it shows, when you actually take your extended sensors, the telescopes, and you look at a small patch. In this case, it's about 10% of the size of a full moon, so a very small portion of the full sky around us. And you just sit there and you just take a very long exposure, stare at this with your telescope, and then this patch, if you just looked at it, would appear very dark. But after a while, more and more and more, the longer you expose, more and more galaxies start to appear. To the extent that in this case, we have about 5,500 individual galaxies in this small portion, as we know. And this is one of the most important lessons for us, that the world is simply full of galaxies. And as you can see also from this image, they come in various shapes, in various features, and some are blue, some are red, and etc., etc. So one of the things that this leads to is that when doing this type of studies, we can know that the galaxy's age, its distance, and the age of the universe, they're all closely related. That is, we see sort of a sequence. And we interpret this nowadays through a hierarchical structure, hierarchical growth model of structures in the universe. Again, a concept that will come back to us many times. And that also means that the study of galaxies here is intimately connected with cosmology, and indeed our course is called Galaxies and Cosmology. And cosmology then is the study of the structure and evolution of the universe as a whole. So if you look at galaxies then, what are major types of galaxies? Well, here you see just a small image of a galaxy group, but going back to the extreme, we can just zoom in on some parts here, and then we see a typical spiral galaxy. And a spiral galaxy, hopefully it's clear what it is. It has its spiral arm, also called a disk galaxy often. We have elliptical galaxies, hopefully clear from the name, it's redundant. They have elliptical forms. They're often redder than the spirals, not always, but often so. And we will come to more distinct features of such elliptical galaxies. And then we have those that don't really fit in. So let's just call them irregular galaxies, say. And this can be, for example, here you see that that's not a spiral, that's not an elliptical. What is it? Well, we call it an irregular. It has some strange sort of shape there. But it is a feature, of course, and it's very important if we study galaxy formation and evolution in a scientific context, to explain why galaxies typically end up as spirals or as ellipticals. And then we have this group of irregulars that that are in between, but there are very many that have very distinct shapes here. Now, here are some images of beautiful spiral galaxies. These are actually taken by Peter, who was a previous student in this course now. He's also an active astrophotographer. You can check out his homepage here for many more beautiful pictures. Some are taken with our telescopes at La Palma. Some actually from the roof of the D building over there, etc. Now, an elliptical galaxy has this spheroidal component, as inferred from the name, virtually no disk component, and a red-yellow color here indicates an older star population. Now, why is that? Well, if we look at the spiral arms in our disk galaxies and our spiral galaxies, they're typically shining blue, and if we do detailed study, we see that there is a lot of ongoing star formation there. A lot of gas present, ongoing star formations. Now, ongoing star formation means that there is a population of these young, hot, massive stars that actually shine a lot in the blue, because they're hotter, So their peak wavelengths are, of course, shifted then to the blue, as we learned during the fall in radiative processes. And when they are around, they also shine. They outshine, even though they're smaller in numbers, they can actually outshine the luminosities in shorter wavelengths. We know this, of course, if you remember from your stellar structure course, that the luminosity of a star increases with its mass, but typically with more than a power law of 1. So for a lot of stars, a good power law is that the luminosity goes with the mass to the cubed, roughly, which means that when you go up in mass, then actually go up even more so in luminosity. You also become hotter, you shift it to the blue, right? But we also know that these stars, they live much shorter. So when the gas runs out, when we run out of star-forming gas in the galaxy and we cannot form any more stars, these young, hot, massive stars, they will die fast. Yeah? They live fast, they die young, and then they will be away, and we're left with this red-yellowish older star population, like the sun, which shines in the yellow, or even more, the long-lived stars that are even less massive than our sun. And those are the ones that are left. And in these type of elliptical galaxies, typically we have very little star formation, and therefore also the galaxies turn bluer. We have used all our gas. Here is another of a giant elliptical galaxies called the seedy galaxies, and they are also called cannibal galaxies because they are believed to grow and grow and grow in size by eating their neighbors, essentially. And that's also, we find this type of giant ellipticals. That's the most massive galaxies we know of in the universe. They often sit in the center of dense galaxy clusters, which are large collections of galaxies that sit together. And then they accumulate more and more mass. They grow and grow until they reach very high masses. And here is one example. This is M87 that sits in the center of the Virgo cluster in this case. So we have this class of interacting galaxies, which could be a leading course for this irregular galaxies that before, that when galaxies collide, this is two colliding spiral galaxies. And here we can sort of sort out that, yeah, okay, if we couldn't resolve this, it would be like a very irregular, but now we can see this in detail. So we can see that it's actually two colliding spirals, right? And such collisions between galaxies are believed to play a very central role, both in the general evolution of galaxies and the galaxy population as a whole, but also in terms of explaining some basic morphology that we see, such as irregulars. Yeah? Often indication of interacting galaxies in some form. Not always, but often. We have several of these things. For example, you know, we live in the Milky Way galaxy, and two examples can be that we are a big spiral galaxy as compared to our closest neighbors, the dwarf galaxies around us, and we're actually eating one of our dwarfs as we speak, the so-called Sagittarius galaxy, dwarf galaxy, the Sagittarius stream. It's like a stream of stars that go from the Milky Way because we are consuming that galaxy. Now, another example of this is that when we analyze the motions of the Milky Way and our nearest spiral galaxy, big spiral galaxy neighbor, the Andromeda galaxy, we're actually approaching each other. So locally here, then with these two systems, we're not following the Hubble flow of getting more and more separated. And this indicates that we're actually on the course of colliding with the Andromeda galaxy. So if we fast forward enough in time, we will likely have two giant spirals here colliding, Milky Way and Andromeda. And such collisions may then also explain why elliptical galaxies often tend to be found where galaxies are closer together, such as in big clusters of galaxies, because once the dust has settled, so to speak, once you have collided, perhaps if you're gas-rich, creating a large starburst galaxy, then, after enough time has formed, if you have similar masses, as we will learn, then you might actually transform your shape. So even two spiral galaxies that collide can turn afterwards into one large elliptical galaxies. Okay? I'm throwing out a lot of terms now, but don't worry, we're going to cover them in more detail, of course, during the course. This is, so to say, the overview. Here is an example of such an irregular galaxy called the Flying Ghost. And it's likely two colliding spirals. Also then, we have the class of active galaxies. And active galaxies then are a little bit different because there, a large portion of the luminosity actually comes from a very small region in the center of the galaxy. Yeah. Also, such galaxies, and that's called then an active galactic nuclear, or AGN. Now, such AGNs, though, sit in the host galaxy, but the core of the galaxy then is way overluminous as compared to, for example, the core in the Milky Way galaxy, centered around the supermassive black hole of our own Milky Way galaxy. And that can be the dominant component, and that means that we can sometimes have extreme luminosities of these classes, and they can be essentially, if we cannot resolve the host galaxies, they're more or less point sources. So the typical example of this are the so-called, that were called quasi-stellar objects. So they were extremely luminous extragalactic sources that were detected, but they looked point-light, so not like the extended galaxies. But they were very, very luminous, and hence they looked like stars, but very, very luminous, so they call them quasi-stellar objects. Nowadays, we typically call such systems quasars. And for example, here again, M87 is a nearby active galaxy, which we can actually resolve the host galaxy. We also see a typical jet coming out of it, which can be another stealth signature of the active galaxies. But if we go to the largest scales, it's exciting now because Webb typically uncovers new quasars earlier and earlier and earlier in the universe as we speak. And I even just a few weeks ago, we had some announcement of a new early universe quasar with a very, very high redshift. I'm not going to quote it. We can just look what it was, but it was about 10. About 10 we had before, actually. So must have been a little bit more than that, even. Now, these active galaxies, we nowadays believe they are essentially, whether it's a quasar, a blazar, a Seyfert, a radio galaxies, that's essentially projection effects to zeroth order. Yeah? And it also perhaps has to do with the luminosity and how we view it. Now, in this, so to say, unified standard model for the active galactic nuclei, then, we have a supermassive black hole in the center and then a small accretion disk around it. And it's accreting a lot from this accretion disk, so we get a very, very high accretion, associated accretion luminosity. So then, here again, the main luminosity of the galaxy doesn't perhaps come from the stars. It comes from the accretion luminosity, from accretion around that central mass black hole. And then we have an obscuring torus, etc., etc. And then with associated jets here, and then depending on the viewing angle, we might see this a little bit different. Now, then you might ask directly, yeah, but okay, we also have a supermassive black hole in the center of our Milky Way. Are we also then an active galaxy? no, we don't believe that we would be classified as an active galaxy, or we wouldn't. We know that, I should say. And that's because the accretion rate upon our supermassive black hole is very small, very modest, as compared to the inferred accretion dates, for example, from a luminous quasar or even a Seyfert galaxy, etc. Again, something we'll come back to. Now, I already then hinted about this. We believe that such then central supermassive black holes essentially sits in the center of perhaps all of the major type of galaxies that we see in the universe. So that's another central component in addition to those that I outlined in the beginning of the lecture. And then the other important component I already hinted, which we also believe is very universal, is that all this visible matter is embedded in a much larger dark matter halo. So the most common galaxy, though, in the universe is very likely a dwarf galaxy. We can infer that most of the galaxies in our universe should be dwarf galaxies. However, I say infer here because when we go out and we look at for example, this extreme deep field from Hubble, right? What we see are the large galaxies because they dominate the light. It's very difficult to detect these dwarfs. We have to be quite close to home, yeah, on the galaxy spatial scales in order to see them. Here is another image of one of the previous students in the class, and here you see again the Andromeda galaxy, and you can see some of the dwarfs here, yeah. But you can easily imagine as we go further and further away in the universe, we see fewer and fewer of these dwarfs, and we're dominated by the big one in the middle in this case, right? So I think that should be a logical understanding. But it is important to remember that most of the galaxies in the universe, if we infer from our local neighborhood, they will be dwarf galaxies, but they don't dominate the light. Now, here is just an image of such a dwarf galaxies, the Sculptor dwarf galaxies to the left here, and you see this loose collection of stars, and the distance is on the order of, in this case, 2 kiloparsecs. And if we contrast this to the globular clusters, they can actually be quite similar in mass, but they have very different radii. The globular clusters, for example, the stellar systems that sits in the halo of our Milky Way, they have much, much smaller spatial extent, as you can see directly in this slide. And also another interesting characteristic is that when you look at the velocity motions of the stars in such globular clusters versus dwarf galaxies, you infer that the amount of non-luminous matter inferred from the gravitational motions for a dwarf galaxy can be extremely high. We will come to this later today, even when we discuss the mass to luminosity radius. So we infer a lot of non-visible, non-luminous dark matter for these dwarf galaxies, but that's not the case for the globular clusters. So, quick question here to see that we're following along. Why does large ongoing star formation lead to a blue-white appearance? Well, there aren't any red or yellow stars. Short-lived massive blue stars outshine the others. The gas in disk scatters blue light out of the line of sight. What do we think? A? B? Some B's. C? All right, it's B. Good, we're following along. We're astronomers, so we like to organize things, classify it, and then structure it from there. The classical organization of galaxies in this case is perhaps Hubble's tuning fork. Here's a modified version of that, which takes into account various ellipticals such as Boschy and Disky. And this is the classical organization where you see that you have the elliptical galaxies to the left, you have the spiral galaxies to the right here, and they're sorted. If you have a bar, you just put them down. If you have no bar, you put them up. And you can also see that an SA galaxy then has actually more dense spiral arms than an SC galaxies. And then we put the irregulars here at the end. It's important to know that this is not an evolution sequence. Yeah? If anything, the evolution would be opposite. But it's not always like that. But the reversed approximation. But this is the classical way of organizing galaxy morphology. And does it have any meaning? Well, you can actually, there is of course a reason for us, just like we like to organize things of stars in the HR diagram, Hertzsprung-Russell diagram, and here we organize that. That's also because the properties vary across this line. And that's, for example, the bulge to disk ratio goes from S0 galaxies to the irregulars, and the opening angle, as we call it, for a spiral arm, or how dense the spiral arms, also vary across this, and then whether you have bars or not. And the physical parameters also vary along the Hubble system. Stellar masses increases typically from irregulars to ellipticals. So irregulars, they are typically smaller in masses, whereas the largest galaxies, the most massive galaxies that we know, are ellipticals on this end. Now, angular momentum, that is rotation, increases from ellipticals to spirals. Ellipticals typically, they don't rotate much, or at least to a lesser degree than spirals. Now, mean age also increases from irregular spirals to elliptical. Mass to light ratio increase from irregulars, spirals to ellipticals. And the color change as well. We have already discussed this, how these are typically redder, these are typically bluer. We will go into some details and on that later. And the cold and the hot gas also, components of the galaxies also change across this indication. There are, of course, complications with these type of classification schemes, right? And one of them is that the same galaxy can look very different in different wavelengths. Here is a very famous multi-wavelength view on the Milky Way, where, for example, if we look here toward the Milky Way center, right, then we see that in the optical here, we don't see much of a bulge. Here we see a very clear bulge in the infrared. And that has to do with this extinction within the galaxy that we also talked about in radiative processes during the fall. That is that the intervening dust particles here, they actually absorb or scatter the optical light that is coming from the bulge out from us, so we don't really see it. Yeah? Get interstellar extinction there. But in the near infrared, they're not very, or in the infrared, they're not very efficient absorbers, such that then we can actually see a very visible bulge here. And if you remember, one of the key things behind the measurements of the stellar motions that around the supermassive black hole in our Milky Way galaxy that led to the Nobel Prize. And one of the main difficulties here was that we had to go away from normal optical observations to the infrared or even radio observations in order to detect this, because otherwise everything would be absorbed, you know. And then from the stellar motions then in the galactic center of these radio observations, of these infrared observations, you can, just using Kepler's law actually in this case, infer that there must be a very large mass sitting in the center of the Milky Way, which is associated then with a compact object or, as we say typically, a supermassive black hole here. Here is another example, and this is the M81 galaxy, where you can see that if we look at high energy X-rays, it looks very different than in optical, and in the UV it looks slightly different again, in the optical again, and in the far infrared. In the ultraviolet we don't see much of a central portion here, but we see the spiral arms very clearly. And again, that gives us a hint to that in the spiral arm, in spiral galaxies, that's where star formation occurs. That's where we have the gas present. That's where we have the young, massive hot stars that can shine more in the ultraviolet. In the high energy X-rays, we can see that we, in this case, just have some emission from the central parts, likely associated with supernova that has gone off or with some outflows. Now, there are other important galaxy classifications that is not contained in the Hubble fork. We already touched upon the dwarf galaxies, where we have the dwarf ellipticals. Well, it's kind of inferred from the name. They're like ellipticals or spheroidals, but they're lower luminosities. We have the low surface brightness galaxies, etc., etc. We also had the CD galaxies, which we also talked about. Extra large diffuse galaxies, ellipticals typically sit in the center of large clusters. And then we have the active galaxies, and then the interacting merging starbursting galaxies, all of which we have already introduced actually. Now, modern classification, though, often use databases like SDSS instead of just the visual that, the classical way is that, you sit here as a professional or amateur astronomer, you observe something, you get to a galaxy, and then, this is a spiral galaxy, this is an elliptical galaxy, etc., etc. Now, there are very interesting sort of community projects like the Galaxy Zoo project that you can check out, where you can actually click and classify the galaxies by yourself. But there are also modern databases like the Sloan Digital Sky Survey, which we will use in the forthcoming lectures, where you can actually design automated fitting according to various criteria and apply that to now much larger statistical samples of stars, and that can give insight into how the distribution of the large galaxy population actually look. And this is then more and more replacing the traditional classification schemes that I've touched upon, right? And it also reveals, as perhaps not a great shock, that it's a somewhat more complex picture than the old standard schemes may first suggest. Now, here is an example of this. This is actually a figure by previous students in class again. This is from an old take-home exam. And that's the distribution of the broadband galaxy probabilities as done from the Sloan Digital Sky Survey. And for example, there to the upper right, you can see the numbers or number of galaxies in this database then, as a function of essentially colors, and there you can see a blue peak and a red peak. Sort of say consistent with this that, well, spirals are blue, ellipticals are red. So even if you look at all the galaxies, you see this blue peak, you see this red peak. However, you also see a lot of galaxies in between, and if we were to be able to classify our own Milky Way, likely we would not sit in this green valley in between. Actually, not on the blue peak. All right, and then you can also, of course, sort this according to then the absolute magnitude, and you can see that if you put this into a contour plot, you indeed get these two, sort of say, peaks, but they're also at different luminosities, which also tells us something. So you can use these type of classification schemes then to gain a more detailed insight into the distribution of galaxies. So here we see in the local universe, then we see that for all spirals, we know we have at least 10 dwarfs, as the current believes. We have some ellipticals. I did not touch upon the lenticulars. That will be for you a little bit of lookout knowledge if you're interested in what those are. They're also quite common, actually. And we have some irregular galaxies, but they're not so many. As you can see, quasars in our local universe are really rare. They exist, but they're very rare. So that's that very luminous quasar. But they actually increase by using, again, for example, SDSS. We can do a very simple exercise and see that the number density, the relative number density of quasars, increase as you go back in time, that is to higher redshifts. Okay, and that tells us again something about galaxy formation and evolution. So this distribution changes as a function of redshift or as a function of time. Now, another thing is that when we look at galaxy spectra, of course, then the peak and the features, they will be different. So this is the integrated spectra from an elliptical galaxies versus a spiral galaxies. And you can see this telltale sign, right? This elliptical galaxies has a peak more to the red. This spiral has a peak more to the blue, as we have discussed. And here is just a slide to say that, okay, as compared to then doing, for example, stellar spectroscopy, when you do galaxy spectroscopy, you have to often work with some sort of pop synthesis models, meaning that we're not getting the light from just a single star here, right? But we're getting the integrated spectra from a full galaxy population. And then you have to estimate the components that go into that. So, for example, you have to assume how much star formation there is, because that's how you can get roughly how many stars of a different sort it is. An initial mass function, how many stars are born with a certain mass. You have to have some sort of evolution track of the stars, again related to this simple fact. You can often think about it in this term that, you know, more massive, hotter stars, they're rarer, but they also live shorter, right? So in order to get, so to say, the integrated vector, and you have to have some sort of assumption about that. And then you can create the synthetic spectra from the stars that make up the population. And depending on your galaxy, you might also need to add some gaseous components there if you want to study, for example, some specific spectral lines, etc. Now, let's go to the active galaxies then. One of the most telltale signs is that an active galaxy has a very different, broad spectral appearance than a normal galaxy. So if we look at, for example, a well-defined elliptical galaxy, we will see that it basically behaves like an old red stellar population with a peak there slated to the infrared and then a very steep drop on both sides. But when we look at these active galaxies, they have much broader components with typically like a peak in the ultraviolet called the blue bump. They can also emit quite a bit in hard X-rays, and then they can be radio loud or radio quiet. That is, either they drop very steeply in the radio, or they actually emit also a significant amount in the radio region. So their spectral energy distribution is much, much broader than that of a typical normal galaxy. Another telltale sign is that they have these prominent, at least if you look at this as a composite quasar spectra, emission lines, or even sometimes so-called P-signal lines in the ultraviolet, of the various features like we see here, carbon-4, we see the H-alpha line very prominently, and these are very broad. Yeah. And again, we will come back to why that is when we discuss active galaxies in that module. So, next thing then, how are galaxies grouped together? Well, first we can call it a group, and the group is typically a small collection of galaxies up to a few dozen per group that are then gravitationally bound, and we indeed belong to a local group. So that's a small collection of galaxies. They can also be sorted against clusters, and we have touched upon this already, but then there are much more galaxies that are, say, gravitationally bound, and there are hundreds to thousands of individual galaxies typically in such clusters. Now, here are two Nearby cluster, this is the Virgo cluster. It's the nearest largest cluster that we know of, more than 2,000 members. Here's the distance, the typical extent of the cluster. It's an irregular cluster here. And indeed, the densest regions here are dominated by ellipticals, as we touched upon. We have the velocity dispersion, which is about 600 kilometers per second. The velocity dispersion here, when we discuss galaxy clusters, we can see how we will see, and in our dynamics section, we will see how we can relate this to the total mass of the cluster. Here is the one of the most luminous clusters known in our local universe, the Coma cluster, distance 100 megaparsec. It's a regular cluster here, and it might have undergone some subcluster merging. It's again dominated by ellipticals. It actually has 2 central CDs, which is also a hint of this subcluster mergings, right? And we have one more in the subcluster. 1,000 kilometers per second velocity dispersion, indicating a higher mass. It's also a very strong X-ray source, as we will see. And these X-rays, which essentially comes from the space in between the individual clusters, individual galaxies in the clusters, which is huge portions of very hot gas there, that can actually also then, as we will see, be used as an additional independent indicator of the total mass of such a galaxy cluster. Again, to reveal, so to say, a main point with these mass estimates is again that we get some sort of indication of the mass to light luminosity radius, and hence how much of non-luminous matter that are contained in these type of galaxy clusters. If we go to even larger scales than the galaxy clusters, then we have these type of famous pictures. Here we see the person in the sky and the Great Wall. And here we see actually one of these structure growth simulations that I have referred to already, sort of a mock galaxy survey using data from this famous Millennium simulation, with the paper indicated there. But you see that these type of large, very, very large structures now, they're typically organized into filaments here, which are filaments of high density regions. High density in this case means more galaxies and galaxy clusters present in those regions. And then we also have like large regions of essentially void or almost void material here. Now, when you go even higher up then, you approach what we call a homogeneous isotropic universe. And when that happens is still subject for scientific research, but it is a basic assumption of our cosmological world models that it does happen on some scale. That is, at some large scale enough, above 100 megaparsecs likely, well, then these type of structures will go away and we will come a statistically isotropic and homogeneous universe like this. Now, this can also then be inferred by the cosmic microwave background radiation, which we discussed in the radiative processes course already to some extent. We gave the background knowledge to that during the fall. This is a picture from Kobe, where first you sort out the peculiar motion, which we will see in the next part here, and then you come to this sort of slide, which is actually very, very homogeneous. It's temperature fluctuations here on the order of 10 to the minus 5, as we know. And there is then, again, the way we typically understand this from, in this case, computer models, is that we go from essentially statistically homogeneous distribution. We zoom in, we zoom in, we zoom in, and then we get in these. These are actually dark matter simulations, right? So these would be the equivalent of a dark matter halo within which a galaxy then, like our Milky Way, will be formed. This takes us then directly to this question of how does galaxies actually form and evolve. Now, deep observations show us that very distant galaxies, as they were much earlier in time, and by doing this, so to say, progressions through time, we can get a sense of how the overall distribution of galaxies may change over time. That is, for example, we can ask, okay, but now when we have a lot of new data from the Webb telescope, does the galaxy distribution of, at say, a redshift around 6, 7, 8 resemble that of the galaxy distribution today? That is, do we also see this type of big spirals like the Milky Way? Do we see giant elliptical galaxies, or do they have different shapes? And that's sort of how we can learn about galaxy formation and evolution by observations through cosmic time. And nowadays, as I said, we typically interpret this through a hierarchical structure growth model, whereby small structures form first and larger later. And it may perhaps be of interest here to note that when I took something like an equivalent to this course, which, was a while ago now, but perhaps not in ancient times at least, then we often discussed that, okay, we have this hierarchical structure model, small structure form first, and then we also have the opposite potential, where we have a top-down scenario, where early in the universe, the largest structures were formed first, and then they sort of scattered down to smaller and smaller. They fragmented to smaller and smaller structures along time, such that we see the type of galaxies that we have today. Nowadays, a lot of observational and theoretical and computational work has gone into this that seem to favor the hierarchical structure growth model as in contrast to the top-down scenario. And again, this is something we will come back to many times during the course. It's also worth noting here the staggering scales that are involved here if you want to study galaxy formation and evolution, where we're spanning something like 23 orders of magnitude in space, from the universe itself to the influence of individual stars, and also 4 magnitudes in times, right? From the universe to the lifetime of the most massive stars. So this is a very challenging problem, and again, we cannot really do all details in one. And I will just mention a few things there, that these are essentially dark matter large structure simulations, where you can form these type of dark matter halos here. But then, of course, if you want to form a galaxy within that, as we saw from our first slide in the talk, then we need stars to form. And how do we form stars? Well, we need these giant molecular clouds of gas that cools down significantly, whereby we can form stars. And that's quite a small scale process as compared to these vast cosmological scales. So to put that into same simulation is, non-trivial to say the least. Now, it turns out that for the general problem, there are other physics processes are critically important. For example, the effect of radiative cooling. Because if the gas is there, but it cannot cool efficiently, then we cannot form these molecular clouds, and we cannot collapse and then form stars, right? And we actually see this type of things happening where we have this type of gas, but it cannot cool efficiently. I mentioned one such situation before when I talked about the gas that sits in between individual galaxies in clusters of galaxies. That gas is very, very hot, and we'll try to understand this by analyzing this, the fact that it cannot cool down efficiently. And then, of course, that gas just sits there and it cannot form any stars in the individual galaxies. But we can use it in other contexts, like in this case, analyze the X-ray emission and then infer the total mass of the whole cluster. Whereas in other circumstances, the gas that sits, somewhere in the universe can cool down, form stars, and then form a proper galaxy, as it were.